To provide an example physical situation, imagine we have some sort of scalar conservation law. So this would consist of some sort of scalar quantity, call it Q, that is explicitly conserved. This could be something like energy or momentum, as an example. So imagine that we have a differential element with a side length of dx by dy. So this is in the xy plane. We can think about what is occurring inside of our differential element. So we will have some rate of change of our quantity within our element with respect to time. And this could be due to two possibilities. One is that we could have a source term. So as an example, if this was energy, perhaps there's a heating source that's increasing the temperature and so therefore increasing the energy. Or alternatively, we could have some flux of the conserved quantity into or out of our differential element. So we could imagine that we have some flux along the x direction in, and imagine we have some potentially different flux called f sub x prime out. And let's say, for simplicity's sake, that we don't have any flow along the y direction. Well, if we think about the three possibilities of impacting our conserved quantity, all three added together have to be equal to 0 in order for our scalar conservation law to hold. That is, a change in any one quantity will necessitate a change in at least one other quantity. So if we think about the flux, the differential flux across our element as an example then. So if we have more flux coming in, or let's say less flux coming in than flux coming out, then we would expect that our conserved quantity will decrease, and so therefore we'll have a negative dq dt term. Conversely, if we have more flux coming in than we have flux coming out, then we would expect our conserved quantity to increase, and so therefore we would have a positive dq dt. And if the net flux is 0, then our conserved quantity would stay the same, assuming that the source term is 0. Clearly, if we have no net flux, but we do have some source term, then our conserved quantity will increase for all time. So we try to express this in some sort of PDE. Well, we have our conserved quantity plus our differential flux. So that means that if our differential flux is positive, so in other words, that we have more flow coming out than in, then our dq dt term will have to be negative. So in other words, our conserved quantity is decreasing. So hence we have plus df dx. And this is going to have to be equal to our source term. And let me just write it as a function of x. So in other words, if our flux increases, or if our differential flux is positive, so in other words, we have more flow out than in, so this is increased, then if our source term is 0 or constant, our dq dt term must decrease. And the converse holds as well.